Good morning, everyone. I hope that everybody's doing great today and that you've had a fantastic weekend. We're heading into a short week. Friday is a professional development day for staff, so there will be no student activities planned for that day. What we're doing this week is finishing up with the current lesson handout. We're going to be looking at the Compton Effect today and Wednesday, and today we're doing Part A, which is just kind of a preliminary to the Compton Effect, and then on Wednesday we will finish it up with Part B. What the Compton effect is the interaction of a photon of radiation with an electron. So in many ways it's similar to the photoelectric effect. In the photoelectric effect, you have a photon which interacts with an electron. One significant difference, though, is that in the Compton effect, the photon strikes the electron and is not absorbed. In the photoelectric effect, the photon strikes the electron but is entirely absorbed. So in the photoelectric effect, the electron gets all of the photon's energy. In the Compton effect, the photon is not absorbed. So the electron only takes some of the photon's energy. There's another very significant difference between the photoelectric effect and the Compton effect, and that's that in the photoelectric effect, the electron is bound to an atom in the metal. In the Compton effect, the electron is free of any atoms. So we say that's a free electron. What happens during the collision is that the electron gains some energy and some momentum from the photon. And this is your first introduction to something which is called wave-particle duality. What Arthur Compton discovered when he did these experiments is that since the electrons gain momentum from the photon, that must mean that the photons had momentum to begin with, which is a little bit of a weird idea because we're traditionally taught that momentum has to do with mass and velocity. And it turns out that photons have momentum even though they do not possess mass. Compton discovered that there's two ways that you could calculate the momentum of a photon. One is to take Planck's constant and divide by the wavelength of the electromagnetic radiation that the photon is part of. And the other is a relationship between energy, momentum, and the speed of light. And if you take the energy of a photon and divide by the speed of light, you will get the momentum of the photon. In these equations, you have to use standard units. So you have to use units of, for momentum, kilograms times meters per second, or newtons multiplied by seconds. Those were the two sets of units we've learned about for momentum. For Planck's constant, you have to use the 6.63 multiplied by 10 to the negative 34 joule seconds version of Planck's constant. You cannot use the one that has electron volts in it. For the wavelength, it must be in meters. In the second equation, energy must be in joules. Momentum has to have standard units, and the speed of light, of course, is in meters per second. So we're going to start off with a few preliminary questions where we're working with those formulas and talking about momentum of photons. The first example asks us to determine the momentum of each of the following. We have a 215 nanometer photon. So the wavelength is 250 multiplied by 10 to the negative 9 meters. If you wanted to put that into standard scientific notation, it's 2.50 multiplied by 10 to the negative 7 meters. Pretty straightforward calculation. The momentum is equal to Planck's constant over the wavelength, which means it's equal to 6.63 multiplied by 10 to the negative 34 joules multiplied by seconds over the wavelength of 2.50 multiplied by 10 to the negative 7 meters. So that gives us 2.65 multiplied by 10 to the negative 27 units of momentum. I prefer the unit combination of newtons times seconds rather than kilogram meter per second. Take a look at B. We have a photon with a particular frequency. Well, when you take a look at your formulas for momentum, which is what this question is asking us to find, you basically have two formulas that you can use for momentum of a photon, and neither one of them has frequency in it. So you have two paths you can follow. One of them is you can use the universal wave equation so that you can determine the wavelength. And if you can determine the wavelength, then you can use the first equation on the left. The other option is to use E equals hf to determine the energy of the photon. And then if you know the energy of the photon, you can use the second formula, which is momentum equals energy over the speed of light. I don't really have a preference here, so I'm going to actually do both. I'm not going to be showing a lot of work in terms of my substitution on paper. So the first thing I'm going to do is use this formula to find the wavelength. If I take the speed of light, which is 3 multiplied by 10 to the 8, and divide by the frequency that we were given, 2.68 multiplied by 10 to the 13, then I get a wavelength of 1.12 multiplied by 10 to the negative 5 meters. And then if I were to use the first formula to calculate the momentum, I would have to take Planck's constant and divide by that wavelength. And I get 5.92 multiplied by 10 to the negative 29. We could do that, or what we could do is go to E equals hf to find the energy of the photon. Remember, you have to use standard units. You cannot use electron volts. So for Planck's constant in that formula E equals hf, we have to use 6.63 multiplied by 10 to the negative 34, multiplied by the frequency, which was 2.68 multiplied by 10 to the 13, which gives me an energy of 1.78 times 10 to the negative 20. And that's energy, so of course it is in joules. Now what I can do is use the second formula, E equals Pc. So P is equal to the energy of the photon over the speed of light. So if we're going to take the second path, we're going to take the energy of the photon, which we've just calculated, and divide by the speed of light. And you get the exact same answer that we got before, 5.92 multiplied by 10 to the negative 29 Newton seconds. C, we have a 10 electron volt photon. Well, this is an energy. And what we need to do is convert that to joules. We know that 1 electron volt is 1.60 multiplied by 10 to the negative 19 joules. That has to equal 10 electron volts over x joules. So we cross multiply. You're going to end up taking 10 electron volts, multiplying by 1.60 times 10 to the negative 19 joules per electron volt. And what you will get is 1.60 multiplied by 10 to the negative 18 joules. So all we did first was we converted that electron volt energy to joules. Now what we can do is use the formula for momentum, which is energy over the speed of light, will give us the momentum. I'll show the conversion. This is the number of joules there are per electron volt. We have to multiply by 10 electron volts. So this is how we're getting the energy that I have written down here on the left. Now what we need to do is divide by the speed of light. And I get 5.33 multiplied by 10 to the negative 27 units of momentum. All right, number 2, X-rays of a particular wavelength are Compton scattered. What that means is the photons in the X-rays strike free electrons, and the electrons get kinetic energy and momentum from those photons. We're asked in this question to determine the wavelength of the scattered photons using conservation of energy. So before we do this, I just want to remind you of something here. When you're talking about photons, and when you're talking about something like an electron, there are different ways for you to find the energy. The energy of a photon is found using hc over lambda, whereas the energy of something like an electron that has mass is found using 1/2 mv squared. So how are we going to use this to determine the wavelength of the photon after the collision? We're going to set up a conservation of energy equation which says the total energy before and the total energy afterwards are equal because energy is conserved during the Compton effect. So what do we have before the collision? In the Compton effect, you have a photon's energy before, and you also have an electron before. After the collision, you still have a photon. Unlike the photoelectric effect, the photon is not absorbed. The photon only transfers some of its energy to the electron. And then we also, of course, have the electron. All right, the left side of the equation is before, the right side is after. Well, the energy of the photon before would be hc over lambda before, and the energy of the electron before is 0. I haven't told you this until now, but during the Compton effect, the kinetic energy of the electron before it is hit by the photon is 0. The electron is motionless. It's not moving. And then afterwards, we have hc over lambda of the photon, plus we're going to have 1/2 mv squared of the electron. Now, we have enough information that you can calculate this because you're told the wavelength of the photon before. So we can calculate that. We also have enough information in the question that allows us to calculate 1/2 mv squared because you're told the speed of the electron. So this is 6.63 multiplied by 10 to the negative 34. I'm going to leave the units out. Multiplied by the speed of light, which is 3 times 10 to the 8. Divided by the wavelength, which was 0.24. It was nanometers, so I'm going to throw in a 10 to the negative 9. And this is going to be the energy before because the electron has nothing before the collision in terms of energy. Afterwards, we're just going to leave this term the way it is, and then we're going to have 1/2 times the mass of the electron multiplied by the speed squared So once again, what this is the energy of the photon before. This is the energy of the photon afterwards, and this is the energy of the electron afterwards. So I'm taking Planck's constant in standard units of joule seconds, multiplying by the speed of light and dividing by the wavelength, and I get for the energy that the photon has before it hits the electron as 8.2875 . 8.2875 . multiplied by 10 to the negative 16 joules. That's the photon's energy before, plus the 0 joules for the electron before, is going to equal the energy of the photon afterwards plus the energy of the electron afterwards. And we can calculate that. So we have 0.5 times the mass of the electron times the speed of the electron. Don't forget to square it. There's a squared on the speed here that's just hidden from view, which gives us 7.58 multiplied by 10 to the negative 18 joules. This should be starting to make sense to you what's going on here, because if I knew the energy of the photon afterwards, then I could use it to find the wavelength of the photon afterwards. Well, it should make sense to you that if you took the energy that the photon had to begin with and subtracted the amount of energy that the electron had afterwards, which is the energy the electron got from the photon, you're going to be left with the photon's energy afterwards. So 8.2875 multiplied by 10 to the negative 16 joules, which is the energy the photon had before, minus the kinetic energy that the electron took away from the photon, gives you 8.212 multiplied by 10 to the negative 16 joules. And that's the energy that the photon has afterwards. And again, that's equal to hc over lambda. So if we take 8.212 multiplied by 10 to the negative 16 joules, set it equal to Planck's constant, times the speed of light, divided by the wavelength. If we cross multiply and then divide, we get lambda equals the 6.63 multiplied by 10 to the negative 34 multiplied by the speed of light, 3 times 10 to the 8, divided by the energy, 8.2112 multiplied by 10 to the negative 16. We are going to get the wavelength in meters. And you get 2.422 multiplied by 10 to the negative 10. Meters, which is 0.2422 nanometers. So what happens during the Compton effect is the wavelength gets bigger. This is the final wavelength. If you were to go back and look at the question, it tells you the initial wavelength is 0.24 nanometers. During the Compton effect, the wavelength of the photon increases, and that's going to be important when we start talking about part B of the Compton effect on Wednesday. So a few takeaways from today's lesson. One, during the Compton effect, the photon collides with the electron, but the photon is not absorbed. The photon glances off of the electron, and in the process, the photon loses some of its energy to the electron. As well, you need to know that the electron in the Compton effect is free and is at rest to begin with. So the electron has no kinetic energy before the collision, and the electron is not bound to an atom in the Compton effect. And perhaps the most significant aspect of the Compton effect is that energy is conserved. We'll talk about the fact that momentum is conserved in more detail on Wednesday. The other thing, of course, in the Compton effect is you need to know how to calculate the momentum of a photon, and you were given two formulas for that in today's lesson. Fairly short lesson, not a lot to it. Complete questions 1 to 5 and 10 on the next page, and then on Wednesday we will finish up with the Compton effect by looking at the second part of it. I hope you have a fantastic rest of the day, you guys, and we will talk to you soon. Take care.